done. This should be done. Okay, should be okay.
Have you done your audio test?
This is a chat. Yeah. Okay. Mana. Students can hear me at home? I think they can.
Yes, we can.
Thanks. That's it. That's it. That's the chat. That's the thing. And it's streaming now. Okay, so let's continue, and I will type some lecture notes that are a bit more pedagogical than the handwritten notes that you had, and also, so this is a roadmap of what we did last time. Oh, yes. Yeah, maybe lecture. Can you not hear me? Okay, I can use this as well. Okay. All right, so this is the rough map, and I'll over this again. So what we'll do today is to finish this to get to the free energies as monotones, and then I'll do some comments and clarifications on the previous lecture, in particular in sufficient conditions. So let me just go through this. So again, on top is thermal operations and the bottom is noisy operations, right? So the first theorem that we saw, and now I only have here one direction, and I'll comment on the significance of the other direction later. So if a state can be transformed to another state via thermal operations, then the vectors of the diagonals in the energy basis can be transformed via a thermostochastic matrix, right? So remember, this comes from just writing, the dephased version of sigma. Yeah, like so, where this is the energy eigenbasis, and these are the corresponding populations. So this is the vector of populations, right? And GB was thermostochastic, meaning that when you apply it to the Gibbs state, you get the Gibbs state again, right? And we saw that for free it comes that then in the special case where all the systems are degenerate, we have noisy operations, right? Noisy operations means essentially you're allowed to apply any unitary and to mix with any fully mixed state. Right? So in this case, if I can transform a state to another, it means that their eigenvalues are related by a doubly stochastic matrix. And just to make the notation a bit nicer, let's just call the uniform vector U. So doubly stochastic means it's stochastic and it preserves the uniform vector. Right? So this is the vector that's just once. Good. Then from here we saw that if two vectors are related in this way, if and only if one vector majorizes the other one. And this, I'll type up the proof a bit nicer. From here, one can define these functions. This is just a definition of true convex functions. It's really, they decrease according to the majorization, right? So if one vector majorizes the other, then this function is decreasing. And you saw in Ralph's lecture, so these are the sure convex functions. Monotones. And if instead of this sign wave in the other direction, then it's sure concave. They're also monotones, and then an example is the entropy. Okay, so in order to transform a state rho through state sigma via noisy operations, the entropy must increase, right? That's an example of a second law. Now, we want to reach the same kind of results for thermal operations, right? We want to find some condition on functions that make them monotones. And so we're going to use a trick, which is actually very general. So the idea is, I want to apply these tools. This worked very well in this case, right? And what I need there is to have that the condition is some kind of a doubly stochastic matrix applied on states, right? If I have this, then I have majorization, and now I know what kind of functions I have. The problem is that that's not what we have, right? We have here a thermal stochastic matrix, which is a matrix that preserves a different state. So what we do is the following. This is state 5, is to look for a mapping gamma or gamma b, so whatever, in the following way. So I'm going to look for a map that goes, this is the dimension of my original Hilbert space. And so the vectors n and y live here, are d. And I want it to go to some other dimension, okay. Large d. We don't know what this is yet. But what I want it to do is to take, so it takes any state to sigma, and it should take my Gibbs state to the uniform state. Okay. And then I want that this is reversible, so I want this map to be reverse and unique. So just u, or actually u over d, which is this vector, just to be clear. 1, 1, 1, 1. Why do I want this? Because if I have this, then I can write a very nice lemma saying that, well, if two states are transformed here by a thermostochastic matrix, then there is a double stochastic matrix here on this side that does the same job. And it's an if and only if. So, okay, it will stay like, no, it won't stay. Oh, was there a trick to keep this down? Or did you find any trick to keep this blackboard down? Or? Ah, okay. It's convenient. All right. So let's write a lemma here. And if anyone is keeping track of what number this lemma should be, let me know. Otherwise, we'll put a big number. I don't think there's any 5 yet. Should be 6? 3. Ah, great. Okay. So there exists a reversible map that goes satisfying in particular that G let me write here linear just to be on the safe side. Is it linear? I don't know if I think it's linear, yeah. We don't need it. Then the two things are true. One, if y is transformed like this in this side, then G x with the matrix defined like this, G is we have this one and 2. If G is Gibbs stochastic, thermostochastic, beta stochastic, then G is doubly stochastic. And the proof of this is very simple and direct. Just find out how to obtain the thermostochastic matrix from the other one. Then Y is X. Now we replace this. X. And now in particular, because this map is reversible, and now this thing here is just the identity, so you can get rid of it, and that's the result we wanted. Yeah, and for the second case, it's just a special case. Where X and Y are G, and you just apply it directly, and you get that. Yeah. Okay, so this is very good. Like, if we find such a map, then we're done, because then, yeah, questions? What did I do?
I think it should be on G and then
Ah, yeah. Yes, this is your G. Yes. Yeah. Yeah.
why in like the formulation of level 3 you didn't include the normalization by D anymore?
I did do the what? Sorry, say again.
Like on the left side you wrote mu divided by D.
Oh, yeah.
But in proof you don't need that.
No, I mean, no, you don't need it because, no, you don't need it because it's linear, because it's a stochastic matrix, right? Yeah. Right, but this is just, okay, no, you can do this directly, yeah. So now if we have this, it's very good and we're done, because then yeah, now we are here, right? Now we have finally a majorization condition, which means that if we can draw like Lorentz curves here and sure convex functions in these objects, gamma of X, then we have our monotones. Whoop. Okay. So we still need to find this map. That's what we'll do next. And it's very clunky. What do I want to keep? Well, I want to keep the other board. This one is too bad. Yeah. Oh no, I don't do close. Sorry. Okay, I'll erase here. So I'll start with an example, and then I give the general case. And really, it's kind of a brute force, ugly thing. So the idea is that we want to map Gibbs states to something uniform. It's going to be in a much larger dimension. And the idea is that we're going to kind of stretch the Gibbs state. So let me give you an example first. try to develop some intuition for this. So suppose that we have a Hamiltonian on 3 states, a Q-trait, and it's such that the Gibbs state is this. So 4/8, 3/8, 1/8. Okay. Let me draw it here. So this is going to be 4/8. Eight, 1/8. And this is a valid Gibbs state. The eigenvalues are decreasing, so you can imagine that you can build a Hamiltonian such that this is exponentially decreasing on the energy, right? Okay. What's D? D is 3. And what we're going to do is to stretch it all the way. So we're going to take each of these cubes of value 1/8, and we're going to stretch them on the line. Okay, like this. So we have here the first 4. And here there are 3, and here's the last one. Okay. In this case, so U/D, the state 1/8. 2, 3, 4. Okay. And large D is this 8. And so we just go, essentially what happened here was to just slice my Gibbs state into pieces such that I can make kind of a big train with all the pieces having the same height, essentially. So if there was a map that did this and was also reversible on the other states, it is kind of okay. We go to a much larger dimension, but it's okay. So now let me tell you what the map in this case is going to be. It should be something that does the following. For any x, which is what x1, x2, x3. Right. 1, 2, 3, 4. So this is the definition of the map in this case, and I'll just tell you what it does to this state. So let's suppose I start with a state. I'll erase here. Okay. I'll give you an example of this, and then we start to understand why this might be a good idea. So suppose x is 2/8, 3/8, 3/8. And remember, this corresponds to the population of the lowest energy level and this of the highest energy level. Okay. So let me draw this. Maybe something like this. Right, this is the x1, x3. And this gets back to the following. So the first get divided by 4, and you get 4 of them. Then the second one gets divided by 3, and you have 3 of them. The last one is divided by 1. You have 1 of them, something like this, not to scale. So what did this do? it kind of gives more weight to the populations of the higher energy levels. Right, you see it here. If I take a different state, so take a state like this, like y is the opposite. So it's, no, sorry, it's this. 2/8, 2/8. Right, to say, if I had this state in thermal operations and this state, I'd imagine I should be able to transform this to this, even if the, this vector has the same numbers, but they're in a different order. But the order matters because, this is the population of the high energy. This is the population of the low energy. So this state is kind of more excited than this. So I should be able to, by thermodynamic operations, to transform one to the other. So in this case, this thing becomes a bit higher here. Here, the same height as before. And this one is like only a tiny bit higher, maybe. Yeah. So I'll give you the general map, and then we'll show you that is reversible. But the takeaway thing is that here, if you look at these two states and you thought about, oh, let's think that now we're in the noisy operation setting. Does this state majorize this one? Then clearly yes, right? This is a much more peak distribution than that one. Yeah. So the fact that you could transform between this and this with a stochastic matrix really maps to the fact that you can transform between this and this with a G matrix, with a double stochastic matrix. So now let me tell you what the actual mapping is. And again, it's not pretty, it's just something that's built by hand to really fit this and make it work. But the nice thing is that we can apply it to many other situations, many other resource theories. I'll talk about this later. So the mapping is the following. First, you have your Gibbs vector, which is a vector of like exponentials, very complicated numbers, which could be real numbers and not even rationals. But we approximate it with a rational vector. Okay, so 1 approximate G. With a rational vector. And we can always do this to arbitrary precision because the rationals are dense in the reals, right? So we just write write the Gibbs vector like this. And this is the same as it was here. And the idea is that all this di belong to n, and that d is the sum of all the di's, right? Just like in this case. And now we make the map exactly like that. So is what? x1 over d1, and then we repeat this. Repeat this d1 times. Then we start with x2 over d2. Repeat this d2 times. And so on, right? We'll end up with this huge vector. Right there was dimension 8. In general, this can be much larger depending on, depending on how horrible these rational numbers are, that they can be approximated like this. So a nicer way to write this is the sum over I, direct sum it's like a direct sum of all this uniform vectors, right? So yes, I mean, maybe it's easier to show like this. Does that make sense? This is just a definition. So in particular, what happens to the Gibbs state? In particular, what happens to the Gibbs state? Well, it's in that form, so I of the I over, so di over d, this was my xi, 1 over di, the uniform vector of this dimension, which overall is just, this cancel out, so it's 1 over the direct sum of just ones is going to be the whole vector of ones. So the total thing, right? Which is what we wanted. Right, because it's doing this, except each of these xi's is just, here you have d1 over d, d1 over d, d2 over d. You get the uniform thing. Okay. Is it reversible? Sure. How do I go from here to here? Well, I'll just take the first 4 blocks and I sum them and I get this. Then I get the next 3 blocks, I sum them and I get this. Take the last block, get that, right? And it's the same here, right? To obtain from this final vector the first one, I just need to come here and sum these values. Right. And yes, yes, that's right. Thanks. So where's page 4? So, to make it more rigorous, it is given by the following. So I need to choose these first ones and sum the value that was there, right? Sum this thing there. So sum the little block there. So the block was the vector pi, the vector element pi. And then I do this. So from I need to see the starting and ending position for this. And what's the starting and ending position? This ji's. Let's I mean, this is just a complicated way of saying I need to see how many of these came before, right? And that's where I start to sum the lines for the next block. So I count all the DLs that came before. So here's 4, here's 3, here's 1. So if I want to go to the last one, it's 4 plus 3, meaning I start at this position. Yeah.
technically the entropy of the two different blocks could do the same.
Yeah, but we know the Gibbs state. This is given. So we know so this map, I didn't want to write beta all along or G all along, or beta, but this map depends on the Gibbs state, right? It's really tailor-made for a specific Gibbs state or for specific Hamiltonian, right? So every time you want to do thermal operations to a different system, you need to build this thing directly. But I mean, later we see an easier way to do it. Okay. So now we have a reverse map, which means that we have now we now have lemma number 6 for free, right? So the step we missed here was that y with this one double stochastic. Stochastic. And then now we have this for free, right? We have a reversible map. So what we have so far is that if I can go from rho to sigma via thermal operations, then this representation of them must be connected like this, right? Which gives us directly, yeah, so it gives us majorization in this much larger space. Yeah. Where's the K? I should be, sorry. K here. Yes, sorry. So each K is each individual cell. The I is the number of the starting point. Yes. Yeah, the I corresponds to this value. Yes. It's correct. Yes. But yeah, it's on the I. Yeah, it's on the index. Yes, I can make it smaller if I'm sure people on the back would thank me. Yes, it's on the I. Right. Otherwise, you'd only be summing over one element. Okay. So now we have all of this, meaning that in principle we are done, right? Because now we can do Lorentz curves on this object directly, and we can do majorization on these objects, and functions that are sure convex on this larger space, right? There are easier ways to visualize the Lorentz curves directly in the original state, and some people like them a lot, so I'll just write it down. I don't have much intuition for them. I'll do it here anyway. 3, 4, 5. Or, yeah.
So I have a question about mapping gamma. The mapping gamma that we found is one that works for a choice of Gibbs state that isn't exactly, it's an approximation to the Gibbs state, right?
Yes, but it can be arbitrarily good.
It can be arbitrary, right. My question is, we then, to this approximation of Gibbs state, we have corresponding the heat stochastic maps, whatever, the G
stochastic, yeah.
Right? My question is, if we have a good, we can have arbitrary approximations to the Gibbs state. Does that also mean that the corresponding heat stochastic maps also approximate the real heat stochastic maps arbitrarily well?
Yeah. Yeah, so the question is that, I mean, depend at what stage are we approximate? If you make the approximation only at this stage, then this is the exact one, right? And this is the approximate conditions. Or you can make the approximation already at this stage, knowing that you do this later. And then and then the results you have is like, this can go to this state, maybe not exactly with this temperature, not exactly with this Hamiltonian, but with Hamiltonian that is very, very close. If we were ever like close enough to this be relevant experimentally, that would be amazing, but yes. But what's the question?
So I guess we could have a case where the X and Y on the right of the if and only if could be slightly different from the X and Y on the left of the if and only if.
Yeah. Yeah.
So,
but I mean, for any epsilon larger than 0, you can make it arbitrarily close. So you just like the closest you go to the larger dimension you go, right? That's the complexity is always the price to pay. Good. So one option would be to do Lorentz curves directly there. One can build Lorentz curves in the small original space. We just need to rescale the vectors a little bit and reorder them and rescaling. So I'll just show you how this works. And we'll not prove that they are the same, but I'll write it down. Okay, so the first thing is to kind of order so I'm here in here, and I kind of want to order the eigenvalues in a way that will reflect their values. So one does is to pick a permutation of them. So if I take the entry I, this is xpi, where pi is a permutation. Pi is a permutation. Such that it kind of orders this thing. So it orders the kind of the height of the columns in the final version. And now we want to build the Lorentz curve. So I don't know if you remember what the Lorentz curves are. Were in this case, they were kind of these points where I had k, and then I had sum for I equals 1 until k of the eigenvalues, right? So I do the same, but I will change the coordinates. Say, so call it a thermal curve of x. I really want them to look like these things here. So, in this case, what would we do? We would order the x in descending values, and then we would plot that thing here, right? And so there would be, the slopes would be something like maybe first a very big jump for this, then it would go 1, 2, 3 at this slope, and then it would go at a much lower slope there, right? Let me maybe make this a bit more explicit. 1, 2, 3. Let's do 4. Right. So we'll do exactly the same, but because we are here, right? So we already reordered them such that we know that this one will come first, and this second, and this third. But now what we'll do is just adjust the x coordinate so that it matches this curve here. Okay, so instead of going here 1, 2, 3 in the x coordinate, we go in a way that reflects kind of the Gibbs population for that energy level. So So look, here is just what we had before. And we just write here that it's the permutation, right? And here we're really just summing how many of these guys we need. And this Z here, it's just a multiplying factor. You could also not have it there, it's the same. Oh, well, no, it's a multiplying factor that is there so that you can compare different states. No, yeah, actually, you don't really need it, no. If you're always in the same subsystem, you don't need it, but in literal case, it's complicated. So what's the result? This will give us essentially the same curve as this. You can try to plot it at home. And then we just, from here, we just define what it means to be thermo-majorized. Okay, so then another lemma, 4 or 5, which is that if, sorry, I forgot the definition. Yep. Definition 4. So we say that X thermomajorizes Y. This is the same as that this curve of X is above the other one, so it's never below T of Y. Okay. And they end at the same time. And same point, which they will naturally. Okay. So this is definition 4, and now lemma 5 is that if those things majorize each other, this is the same as saying that X thermomajorizes Y. And the way to prove it is really to just go, is really to just show that these two curves are equivalent. They give you the same thing. The only difference is that this one has some extra points there and there, and you can like get rid of them with some machinations. Okay. So we made it. We made it all the way here, and then one just defines from here. Now we have a condition, which is we know how to check. We can either check it in a larger space, or you can build a Lorentz curves and check in the smaller space that this is satisfied. And this is a definition of so Thermo-sure, Gibbs-sure. Convex functions, right? And then you saw in the tutorial that examples of this are the free energies. And that's how we get, even without knowing anything about physics, you did not need to know any thermodynamics before. Just from the very simple thing of, well, I allowed for unitary that preserve energy and for mixing with a Gibbs state. Just from this set of operations, you get to, oh, look, the free energy must always decrease. And you have different variations of free energy, and this is a family of monotones. I wanted to comment a bit on what happened in this direction in the first theorem. So in the case of noisy operations, it's an if and only if. So if there's a stochastic matrix, then for every delta larger than 0, we can build a valid noisy operation that transforms between the two. But in this case, that's not what the result says. So if you look at the statement of the theorem, what it says is that there is a thermal operation that acts in the diagonal in the diagonal values in the same way. But we still have the problem of coherences, right? What happens to the off-diagonal values? It's just because it's valid to transform their diagonals, it doesn't mean that that you have all the freedom to create coherences. One example is if you have this kind of Hamiltonian, you cannot go, for example, from state 1 to state plus via thermal operations, even though this state, what is this state? It's sorry, 0, 1, 0, 0. And this state is so clearly, like, if you're just looking at the diagonals, then this would be like the fully mixed state. So clearly you can go from the excited state to the fully mixed state, right? But because of these coherences, you cannot do this transformation. And all this talk about coherences is something we'll cover later after the holiday when Ralph gives me a lecture. Maybe. Good. And one more thing I'll tell you before you leave is that this procedure that we did, like the annoying thing that we did today, this you can do in most cases when you have a resource theory that preserves only one state. There's only one free state, that's the fixed state, right? Does not need to be the Gibbs state. It could be something else. And then this leads you to this to this G preserving stochastic matrices. Then you can always find this map exactly in the same way that we did before, that we did today, right? There was nothing special about temperature or energy or nothing here, right? We just started from this G approximated by a rational, and then suddenly we had a stochastic theory, a double stochastic theory in a larger space. So you can do this with any resource theory, and then you'll end up with something like that. And we'll talk more about generalizations and constraints of resource theories again after Easter, because next week it's Marco. Sorry about the change of topics, but it's about when the lecturers are around than anything else. So I'll be in the room, I think, next week. So Mark will talk about quantum learning. And that's it. Good. See you next week or in office hours. Let me just stop the video.